Hi everyone! Today we're going to discuss the difference between microstates and macrostates. Now this distinction is going to be very important if you want to understand how you go from statistical mechanics to thermodynamics. So first, what are microstates and what are macrostates? So in physics, whenever we have some system and it's in some particular state, there are actually two different ways we could describe it. One using its microstate description and one using its macrostate description. Now, they're called microstates and macrostates for a reason. Microstate suggesting very small, macro is sort of large. So the microstate description is the description that really contains all of the information. If you have, say, an ideal gas and you have a bunch of particles, the microstate description tells you about all of the microscopics. It tells you about the positions of all of the particles, their velocities, their individual energies, all of that. Whereas the macrostate description of a particular state is a little bit more coarse-grained. It tells you a little bit more about sort of just the large-scale macro structure or macro properties of the system. So in order to understand these a little bit better, I thought the easiest thing to do would be to look at a couple examples to see how this plays out. So let's first consider the very sort of simple example of 3 coins. So we're going to have these 3 coins and we're going to flip them right in front of us, 1, 2, 3. And then of course each one will end up being a head or a tails. And whether whether 1 is a head or a tail, 2 is a head or a tail, 3 is a head or a tail, all of that information is going to tell us the state of our system. So let's first consider the microstate description of sort of these heads and tail flips. I should mention this example would apply equally well if you wanted to consider, for instance, particle spins. So we could have a particle and it could have a spin up or a spin down. And you could think of heads as being like spin up and tails as being like spin down. So if you want it in the back of your mind, think about particle spins. That works equally well. But for now, we've all dealt with flipping coins before, so we're going to stick to this more sort of tangible example of coin flips. So let's write down all of the microstates that you could have that would be associated with your 3 coin flips. So the first one you might have, for instance, right, would be the 3-head state. So this is sort of the unlikely state where you flip it and every single state gives you a head. Next, you could of course have 1 tail, so you could have head, head, tail. But then of course, maybe, so here I wrote it as the third coin is the tail, but maybe one of the other 2 coins could have a tail. So you could have head, tail, head, tail, head, head. And then similarly, we could have 2 tails and only 1 head. So we could have tail, tail, head. Oh, that got a lot brighter. Okay, now you can see a lot better. The magic of LCD lights, little lights. Great. So we could have these 3 states where we have 1 tail. Similarly, we'll have 3 states where we have 1 head. So we could have tail, head, tail, head, tail. Sorry, this is getting a little long. This is the last one, I think. So the 3-tail state. So these would be called the microstate descriptions of our 3 coin flips. Now, on the other hand, maybe we don't care, which particular state was the one that was a tail. We just care about how many states, how many coins were heads and how many coins were tails, and you don't care which one was which. Then you might want to write down the macrostate description. So the macrostate description, is just, for instance, maybe it just tells you the number of heads. So we'll see this first state is 3 heads. And then these next 3 states, they all have two heads, and so they all will have the same macrostate description. So these are all the two heads states. And then the next three are the one head states, and then the final one is 0 heads. And so you'll see that this macrostate description is much more coarse-grained. You're sort of losing information. A macrostate description always has less information about the particular state than the microstate description. But a lot of the times, let's say we had, Avogadro's number of coins, maybe we don't care about tracking every single coin and seeing which coin is head and which coin is tail. Maybe you just care about how many were heads and how many were tails, and then that macrostate description is just fine, and that tells you enough information about your state, and you don't care about the details. So on that note, let's look at one more example. So let's consider an ideal gas. So an ideal gas, like I said, we know is made up of generally, tons of particles. Like I said, maybe Avogadro's number of order particles. So let's consider some ideal gas. So we just have some box, and there's a bunch of particles in it, and they all have some little, so each one is going to have some little velocity. Let's say the ith particle has velocity vi, and then we could, each particle will also have some energy ei. It'll have some position. If we want to describe our ideal gas, then we could have all this information. We could also, for instance, consider sort of the larger scale properties of our ideal gas. We always talk about things like the volume of the container that it's in. Now this is a big V for volume, little v for velocity. We could talk about things like the pressure, the temperature. All of these properties we could also use to describe our ideal gas. So now let's think about which of these properties are properties that describe the microstate and which one are properties that describe the macrostate. So the microstate properties, again, so these are the properties that really, if you know the microstate of this ideal gas, what you should think in the back of your mind, if you know the microstate, that really means you know all of the information. You can actually always deduce the macrostate properties if you know all of the microstate properties. So these are going to be things like the particle velocities. And so really the individual particle velocities, not the average velocity, not the RMS velocity, the individual particle velocities of each one. The particle energies. Of course, you know that if you know all the particle velocities. You could compute the kinetic energy of each particle. The positions. So these are all sort of, if you wanted to know exactly everything that's going on in this ideal gas, you would have to track every single particle and say, what is this particle's velocity? Where is this particle? And then a second later, they all will have moved, and all of this information could have changed by a little bit. But so these are sort of the sort of things that you would track if you were considering the microstate of your ideal gas. But this is a lot of information. So instead, what we might care about is only knowing the macrostate of your gas. So again, this is something that's a little more coarse-grained. It just tells you about larger scale properties. And in the same way here, where we found that multiple microstate descriptions are associated with the same macrostate, the same thing applies to the ideal gas. So the macrostate are things like the pressure, the temperature, the volume, the total internal energy. And then like things like the RMS velocity. These are all macrostate properties. Again, we could continue the list, and I'm sure there are lots more we could write down. But what we find is that you could consider all sorts of states, all sorts of microstates, where each particles have, particular particle velocities, where many of these microstates will be associated with a state with the same total pressure. So, for instance, maybe if you have a totally isolated system, then second to second, its microstate description is changing. The particle positions are changing. This one's going to bounce off against this wall, and its momentum is going to change. The microstate description is changing instant to instant, whereas the macrostate description could be staying the same. If it's in an equilibrium state, then you can have a well-defined pressure and temperature, and it's isolated maybe, and these things are not going to be changing in time, whereas the microstate is going to be changing second to second. So in most cases, when you're dealing with things like ideal gas, where you have lots of particles, this macrostate description is not only going to be enough, but it's really just going to be a much more useful description of your system. So to recap, let's think about sort of 3 takeaway messages about the differences between microstates and macrostates. So first, it's really that microstates contain more information, or really all of the information about the state. So you have a system in a particular state. If you have the full microstate description, then you really know everything about the state. Whereas if you only have the macrostate description, you lose a lot of information there. 2, what that also means, and so what we saw really explicitly here, is that generally there are multiple microstates associated with each macrostate. So multiple microstates associated with each macrostate. So like we saw here, we could have the microstates of 2 heads, it's really the macrostate of 2 heads, and then you'll see here there are 3 different microstates associated with that one macrostate. And then the third thing, and why we really make this distinction, is when you have many degrees of freedom, so many particles, many things that you could write down for your microstate, the macrostate is often more useful. And again, that's because often, like in this case of the ideal gas, the microstate is changing from second to second, whereas the macrostate might be staying constant. And so really it's a much more useful thing to talk about. So hopefully that helps to clarify for you guys the difference between microstates and macrostates. As I said, understanding this distinction is going to be very important in starting to understand things like especially entropy, or all sorts of things like these thermodynamic things, and understanding how they arise from microscopics. So thanks.